So today's topic is one of the more mysterious issues in the universe, black holes. One of the most exciting ones too, because as I will explain to you, we have recently actually measured them directly for the very first time after their prediction 100 years ago by Einstein. So this is all very exciting in the field of physics. But let me take you through some of the ideas that have to do with black holes and where the black holes come from and what they may be. What are they? It's curious. This is one of these terms invented for astronomy that has taken over the popular culture. So I don't know, even in your private lives you may have black holes, but certainly in the world of politics and administration and companies, the word black hole is just is used commonly to describe various things. Okay. So here we have a sort of a vision of what might be falling into a black hole from a cartoon. This is sort of interesting because this sort of illustrates one of the more profound points about a black hole. I'll explain what it really is in a moment. But it's an object where things can fall into, and some things do come out in the end, but they have absolutely... It doesn't matter really what goes in. You can imagine, rubbish or people or, fine cars, a Rolls Royce or a crashed, a wreck or something. They fall into the black hole, and it's true, as they fall in, they get broken up and their energy that's released in their breakup, that comes out. But it has nothing whatsoever to do with whatever went in. You can't tell at all when you study black holes, and we do, because they're not as black as you might think. We know nothing about what the details of what went in. All that gets destroyed completely from in the outside world. It's the ultimate, if you like, garbage destruction machine, pulverizing machine. So, what then is it that we can actually look at? So here is a depiction of something that's black in the middle, and here's a star. Okay, and so this star is being disrupted by the enormous gravity force of this black hole, and it's a companion. This once was a companion star that collapsed into a black hole. I will try to explain to you how this happened. But it's being pulled apart, and this gaseous debris is falling in, circling around. It's got a certain amount of, this thing is orbiting, so there's this angular momentum. It forms a disk, and eventually all that stuff goes in and becomes invisible. And it's while in this state of being disrupted and falling in that this gas gets very hot and shines in X-rays. And that's how we can determine there's something shining there, and in the center of what's shining, giving this the energy of all this gravity in here, and that's what we call a black hole. And it's the remains of a star that was too massive for its own good, perhaps. It collapsed, and something invisible was ultimately that's left behind. Okay, so this was once a star. Maybe 100 times more than our sun. And so we've been observing these for, we call them candidates for black holes, because there's no proof that this really is something black, just some enormous gravity field disrupting this material is what we see. But there's also another realm in astronomy where we see things that we are pretty certain are black holes. And that's in objects like this. So this is a whole galaxy, and it's busy having some enormous eruption. And this is hot gas seen with telescopes. The blue is X-ray emission. The ordinary is the red and the white are just optical light. So we have images of the galaxies like this, often taken from space to get this exquisite resolution. And what is the source of all this outpouring of energy? Well, we are convinced that because this energy comes out from a very compact region, and also because the energy output from the compact region, it's enormous, it's brighter, in fact, than the light from all the normal stars, which are out here in the galaxy. Something quite luminous often occurs in the middle. And there's so much light coming out that we call these things, often they're called quasars, versions of this, more extreme than this, in the distant universe. They're the most brilliant things in the universe, the most luminous objects in the universe. And also, another curious thing that convinces us they're so compact is that all this energy comes out from a tiny region, because the energy often varies over the course of years or even months or even shorter. And this means that to get these variations, the compactness of the region must be just a matter of light months, light years, or light weeks across. Now, when I say things like that, you have to remember the galaxy itself is tens of thousands of light years across. So you have a region that's much smaller than the galaxy, the very center, which is shining more light than the entire galaxy. Anyway, we think this has to be a black hole as well. But in this case, this black hole, if it is responsible for this, is weighing millions of times the mass, or hundreds of millions of times the mass of our sun. So these are monster black holes. So we have strong evidence from astronomy for black holes of stellar origin, massive stars. Our sun will not become a black hole, fortunately, but more massive ones around us might. But also from maybe the mixing, the merging of many stars to form this enormous thing in the middle, to form this giant black hole. We see both of these things in the universe quite commonly, and I'll try to tell you a little bit more about how we can actually measure and confirm the presence of a black hole there. So, okay, so what is a black hole? So here is a quotation from the person who really popularized the name black hole. He wrote the following: "It's a completely collapsed object. It's mass without matter." Okay, you can't see the matter. "The Cheshire cat in Alice in Wonderland faded away, leaving behind only its grin. A star that collapses to make a black hole fades away. There remains behind only gravitational attraction, the attraction of disembodied mass." That's all you feel in the outside world, the attraction, the gravity force. You can't see anything directly, unless you catch the stuff on its way in when it heats up. That's a byproduct. Okay, so what am I going to tell you about then in this lecture? I'm going to talk about the discovery of black holes. Very recent phenomenon this year, early this year. I'll tell you about the predictions, which go back a long time. I'll say a bit more about the types of black holes that we have in astronomy. And finally, observing them, and then the searching for the monster black holes and the quasars. So that's what I want to tell you a little bit about. Okay. So gravity is really an amazing force. I mean, you can't see it. But, it keeps us on the Earth. It keeps the moon, going around the Earth. It explains the tides in the oceans from the effects of the moon on the Earth. It explains why the Earth goes around the sun, why other stars orbit each other, even why the universe expands. So all of these things are the effects of gravity. And the main thing you learn from this is because it applies both us on the Earth, far away in space, it's some sort of universal law, and that was Isaac Newton's great contribution to this. Remember, he was supposedly sitting in an orchard, an apple fell on his head or something, and he sort of suddenly had an insight, said, aha, that explains maybe the force of the apple on me, that the Earth has gravity, but the Earth also attracts the moon, so it's not valid just in my orchard, but also on a scale of millions of many millions of kilometers. So, and beyond for the distant stars, which he didn't know about too much then. Okay, so if you imagine the end point of the sun, it will collapse. When it runs out of energy, it'll collapse in probably what we call a white dwarf star. But if I had a star more massive than the sun, it will collapse all the way. A white dwarf star is supported by atomic forces, but if you have enough gravity there, enough mass initially, those atomic forces can't stop the collapse. You end up with a black hole. And a black hole which, for example, had the mass of a star like the sun, would have all the mass of the sun, which is, a million kilometers across now, but compressed into a tiny sphere of about 4 miles. Okay, so, and that means when you make this solar mass object so small, it means the gravity force becomes incredibly strong. I mean, we feel gravity on the surface of the sun. If you go to the surface of the sun, you feel the gravity from all the stuff that's a million kilometers down below you. But if you're on a mass like that, that's 4 miles across, you're feeling all that same mass giving you this incredible force of gravity over a much smaller region. So it's much more intense. In fact, it is so intense that light can no longer escape. Before it collapses, light can get to you. You can see the light doing more and more work against this collapsing sphere, this strong gravity field. That's what the theory says. When the light has a hard time escaping, it loses energy, gets redder and redder and redder. But eventually, at some point, if this object collapses to a black hole, the light can no longer escape. And that final disappearance of the light, from which there's no point of return, is what we... it's like the ghost of the soul that's left behind. We call this the event horizon, the final distance that you can never, in principle, ever get any light from. Beyond that, light is just deflected back in, light doesn't escape. Okay, so this universal law of gravity that I mentioned that Newton discovered first. So he noticed that, to explain the apple falling on his head, to explain the moon orbiting the Earth around the sun, Earth around the sun, etc. The gravity force just gets weaker with distance, and it falls off as the distance, what we call the inverse square law, in fact, is the distance squared. And this seems to explain phenomena on all scales now we realize in the universe. But Einstein was not happy with Newton's version of gravity, and I'll see a little bit why in a minute, because there was a long time problem with gravity theory of Newton that it couldn't explain one or two astronomical phenomena. The most serious one was, astronomers in the 18th and 19th century were great at observing the orbits of the planets, and they obeyed Newton's gravity, what we call Kepler's laws, all this stuff very, very well. But there's one exception, and this was the planet Mercury closest to the sun, and that had a weird anomaly in its orbit that had been studied for centuries, by astronomers when they first brought their telescopes to bear and measured its position carefully. And there was a funny offset, and they said, well, maybe there's some planet inside the orbit of Mercury. Mercury's the closest planet to the sun, which is perturbing its orbit slightly, pulling it slightly around, because it'd be going around more rapidly, the sun. And they named this hypothetical planet Vulcan, and many decades were spent searching for this hypothetical planet Vulcan, more massive than Mercury, to account for its effect on Mercury's orbit. And it was very frustrating because every now and then there'd be typically some amateur astronomer would provide evidence that he'd seen this, and then other astronomers would rush in and follow this up. One or two would find something, but most of them would find nothing. And so this was sort of like a wild goose chase, actually, that went on for a long time, and no one ever found Vulcan. And it turned out to be an example of a useful hypothesis based on what was then known in physics, but was just wrong. And it motivated Einstein to come along with his new ideas about this. And what Einstein said, Newton's theory does not apply with enough accuracy to explain this. There's something else going on. And he said that really you can't just treat objects as just moving around as bodies in space. They have an effect on space. So the essence of Einstein's new vision of physics, of gravity, was that the space, and it's really a combination of space and time, because time goes on and things move from one point to another, it's the space and time that accounts for the motion of matter, maybe in orbit around a star or whatever, and the effect of the matter is to make space slightly curved. Normally in space we talk about Euclid's, view that triangles or three angles add up to 180 degrees. That is not correct anymore in Einstein's view. There's a very slight deviation. And it's the effect of having extra gravity force that curves space more. And if you were very close to an extreme gravity force, like a black hole, which Einstein predicted should exist in principle, then you may get a very hard effect. And then suppose there are such things as extreme gravity forces around these completely collapsed objects called black holes, then Einstein imagined that, maybe something could come along to shake this, another black hole might fall in, a star might fall in, something might happen to this black hole to cause it to wiggle a little bit, okay? And that wiggling of the black hole has the effect of generating what we call gravitational waves, little energetic pulses changing the gravity field go through space, just like sound waves are generated, by vibrations in electromagnetic fields. You can generate, sound waves and electromagnetic waves, whatever. You watch television, all this stuff. But you can do the same thing with gravity. And so you can think of these as slight ripples in space and time, producing gravity waves, and they carry energy away as maybe these two black holes merge together. And that was the amazing discovery that happened this year for the very first time, 100 years after Einstein's prediction. So anyway, I'm running ahead of myself, but let me go back another century or two. And this is now the 18th century. So here is John Michell. So Michell was professor of geology at Cambridge. He was the first person to really to measure the detailed geological structure in the UK. He made many maps, which are still the basis of many modern maps used today. And he was one of these people who had very strong interest in the natural sciences and other things. And so he spent some of his career as a professor in Cambridge, and then he went on, became a vicar in Yorkshire for the rest of his life. And there he was freer to speculate even more about interesting things. And this is what he wrote. So he was the person who predicted that there should be black holes. So what he said was that if the semi-diameter of a sphere of the same density as the sun were to exceed that of the sun by 500 to 1, a body falling from infinite height towards it would have acquired at its surface a greater velocity than that of light. Okay. And then if you expect light to be attracted by this same force, then any light that will be emitted from this huge concentration of gravity force would not escape, would have to return to this object. Anyway, so let me, and so he wrote this published this in the 18th century. And so the argument he gave, it's simplest to think of it this way, is if the star is too compact, light cannot escape. That was his idea. And what he simply said was, so this is meant to be, m is the mass of the star, is the size of the star, and this is the speed an object would have when it falls towards the star. So for a given mass, the smaller the thing, the greater the speed, it speeds up. And he said if you make the stars too small, the light simply will go so fast, even something with the speed of light cannot escape. It just fall into the black hole. So that was John Michell's argument. So he also made another amazing prediction. He said, well, how on earth can you test this? He said, well, imagine two stars in orbit around each other. I can, in principle, he said, imagine a binary star. These are two stars. And one of these, if this were massive enough to be a black hole and nearly a black hole, it will be attracting stuff, pulling stuff out of this other star. And that, he said, might be an observable thing, to study binary stars. And measure their motions and test if they could ever have a region intense enough, one of the stars you couldn't see, that might be this thing so black light couldn't escape. This is sort of the modern version of what he might have said, namely this so-called black hole is pouring stuff in, the stuff would heat up, and you'd infer there had to be some gravity force so great there had to be a black hole. Okay, so John Michell, 18th century. And so things got stuck there for a long time, and the person who set the black hole into place, as it were, was Karl Schwarzschild. Now, he was a German scientist, and when he was around 40, he was fighting in the First World War, and he died, actually, in 1916 from a disease he caught in the trenches, I guess. And nevertheless, a year or two before then, I think he was actually in the army at the time, he had this amazing idea. He had read Einstein's paper on the prediction that matter is curved, the gravity curved space. That's what Einstein said. And he said, well, he calculated for the first time the size that Michel had speculated about of this object that was so compact that light couldn't escape from. And we call this now the Schwarzschild radius after him. And it's just basically the mass of the black hole divided by the speed of light squared. And this is a scale. And if you know the mass, then you know what this scale is. So for any mass star, you know what black hole it could form. It's very, very small. It's 4 miles from the mass of the sun, as I said, incredibly small. And so this is how space is being curved. Imagine space is basically uniform. You can think of this in this projection as being flat out here. When you get near this black hole, space suddenly starts deviating from its flatness, if you like. And then as you go inside of it, there's this region from which light can never escape. And then way inside the black hole, a region that we can never see because we can't see inside, Einstein's theory predicts that there should be something called a singularity, where all physics might break down. And this is one of the great mysteries of the whole field, namely, if this did happen, what would the consequences be? But of course, we can never see it, so we're protected, which is a good thing, okay? There was a similar argument made that the effects of light could be curved as they propagated through space by a great enough mass, as they went near maybe a black hole, or a star even. And this was another physicist, this guy in the 19th century, really. So he said, well, let's go back to Newton's theory and imagine light going by, there's the star over here. And so in his view, at that time, one thought that light was corpuscles made of particles, light particles. He said, well, they would feel the effect of gravity. They might have a very tiny mass, and therefore, that as they went by the sun, they should maybe have a slight curvature. And so, and he predicted this, okay? And in Newton's theory, he predicted a certain change in the angle. So if you can imagine looking at a star over here, way behind this star, then if this star was moving relative to the distant star, then as it approached, you would sort of see the distant star being displaced slightly, right? By the effects of the bending of light that even Newton's theory had predicted. But it turned out that Einstein had a different view of things. And so he, first of all, confirmed this idea that Newton's theory works. Okay, let me wake up my machine again. And as is typical these days, but maybe less typical in those days, he didn't even cite Soldner as having made this prediction, okay, whatever it was. But then this was when he was developing his initial theory, which is not a theory of gravity, of relativity. And then in 1916, he used the new theory of gravity, which was highly mathematical. Very few people understood it. One of the few people I'll mention in a moment who understood it was Arthur Eddington, a British astronomer. And when, a few years later, a journalist asked him, Mr. Eddington, I understand that only 3 people in the world understand general relativity. And Eddington replied by saying, well, I can just think of 2 of them, meaning himself and Einstein. So it was an obscure theory, and this was after what we'll come to in a second, its verification. Anyway, so Einstein then used this new theory to predict that the effect on the deflection, if you remember before, Newton's theory had a factor of 2 in front of this number, it doesn't really matter, but Einstein predicted double the size of the effect for a star behind our sun, or any star, being deflected by the star getting close to a view of that star. So this was something that one could actually go out and measure. So this was 1916, he made this prediction. So his paper went indeed to Arthur Eddington, who's shown here, and Eddington, who was the director of the Cambridge Observatory from 1910 or so onwards, and for many years thereafter, he had great insights into how the world of stars worked. And before he'd even read Einstein, he was understanding why it is that stars shine. And one of his most intriguing statements, and this is fundamental to understanding of stars, is that to understand why stars shine, you don't need to really get to grips with the messiness of the thermonuclear reactions that go in the center, hydrogen burns to helium, that creates energy, just like in a bomb, that makes us... He said they didn't know this at the time, but Eddington was able to show by simple gravity arguments and arguments to do with radiation, pressure supporting stars, that he said, imagine a physicist living on a planet with all clouds all the time, you can never see the stars. This person could predict that there had to be stars, just because the laws of physics would tell you that stars had to exist. Anyway, so Einstein wrote during the war, just at the outbreak of the war, to many astronomers, telling them he had predicted this deflection. And he said, well, the sun, go to the sun, imagine an eclipse of the sun, then maybe you should see the position of the stars far away behind the sun. They should not be, they should be deflected slightly. And that should be a way of measuring space. And then, so he first gave the old number from Newton's theory, which was, totally wrong. But then when he worked out his new theory in 1916, he predicted double this value. So this was the value, general relativity, the new theory of gravity, matter curve space, space curves light, etc. That was what he predicted. Okay, great. So Eddington was a Quaker pacifist. So he didn't want to be conscripted, go to fight in the war. So he was able, by working closely with the Astronomer Royal at the time, to lead an expedition to West Africa, the Isle of Principe, 1919, where there was a total eclipse occurring that year, and he was going to measure the deflection of light of distant stars during that eclipse to try to verify Einstein's prediction. And because one is never too certain about weather, etc., they went to another place in Brazil where also was in totality for the eclipse. A second expedition went there. So Einstein predicted this tiny deflection, 1.74 seconds of arc. I mean, the moon or the sun, is 30 arc minutes across. This is a tiny, tiny effect. It's roughly, if you see stars flickering in the sky, this is roughly that sort of flickering, or what you can resolve, a planet might be. It's a little bit less than that. But it was, with a telescope, once you were able to do that. And these were the results that came out from the two expeditions. But from Sobral and Principe, that is, they were getting numbers that were definitely close to what Einstein had predicted. But let me just tell you some of the stories that go behind that. So this is an excerpt from Eddington's diary at the time. It's really an amazing story of how we do science. The eclipse was due to occur at 2 o'clock in the afternoon, 29th of May, 1919. But that morning there was heavy rain in Principe, which is off Africa. Eddington wrote in his diary, the rain stopped about noon, about 1:30. We began to get a glimpse of the sun. We had to carry out our photographs in faith. I did not see the eclipse, being too busy changing plates, except for one glance to make sure it had begun, and another halfway through to see how much cloud there was. We took 16 photographs. They're all good of the sun, showing a very remarkable prominence, but the cloud has interfered with the star images. The last few photographs show a few images which I hope will give us what we need. However, he did manage to get several plates, and over the next week, he developed the plates. Almost all were of poor quality. He eventually recorded in his notebook that one plate I measured gave a result agreeing with Einstein. So the other expedition, to measure the same eclipse from Brazil, far away, different weather, they had much better luck. They had far better observing conditions and generated more than 20 plates. However, more than half of these gave a larger value than predicted by Einstein's theory. Eddington realized that smearing by the atmosphere would tend to exaggerate this place. He was thinking this is the flickering of the stars, When you look at the sky, if there's a bit of turbulence in the air, it's normal, it happens all the time. This gave him a good reason for dismissing the larger values. So he threw away some of the data, okay? He rejected the outlying points, and only used the results from the South American expedition that agreed with his data. Well, that's an interesting way, and we still, some of my colleagues do science the same way, but it's whatever, but most do not. anyways, this is the sort of prominence that they saw in an eclipse. The amazing thing, the sun is being blocked out by the moon, so you can see these very faint features in the corona, and what Eddington and the others were looking at with these faint stars that you could see displaced by a couple of arc seconds from the normal places. Okay, so 1919, the world was recovering from all the gloom of the First World War, and this made front page headlines all around the world. Lights all askew in the heavens, men of science agree more or less agog over results of eclipse observations, Einstein theory triumphs, stars not where they seemed or carried to be, but nobody need worry. Nobody, no more in all the world could comprehend it, said Einstein, when his daring publishers accepted it. Right? Okay, so onwards. Now let's move on to the much more extreme case where you have a black hole. So the person who established the name black hole in the scientific and popular literature and beyond was John Wheeler, a physicist who just died a few years ago. And this is an interesting demonstration of the curvature of space. You can see Einstein's image here. So this is where the black hole is, and you can see how space gets distorted. So this is the conceptual idea that of what a black hole does, and this is another example of this. And as Einstein said, that this is the effect of matter, which is curving the space, and you can think of that as what matter then does is being moved by the space. So if this were light, then light is reflecting the bending of space, and so no longer goes in a straight line. If the light went over here, it would move in a straight line, space is flat. When it goes through this warp in space and time, it's bent. And here's another view of that bending. And so now let's imagine that there's a distant galaxy over here. Here's our telescope. And the light from this distant galaxy is now going to feel, there's a lot of gravity in this galaxy. A lot of it turns out to be what we call dark matter. And so, there are light rays that certainly go straight through, but many of them will pass in this direction, and then they will feel this extra warping of space and turn around and come back. And so if you imagine the image this telescope takes of this background galaxy, well, it might see, the galaxy, if this is transparent, it can maybe see right through it, depending on how adjusted it is, but it will see the light from this spread out. And if you think about this in 3 dimensions, it will be like a ring. And amazingly, this is what we've been observing for the past decade, especially with instruments like the Hubble Space Telescope. When you look at very distant galaxies, and this galaxy, this is the nearby galaxy with a large, what we call a halo of dark matter around it, the light from this galaxy, which you measure from the registry, way, way more distant than this galaxy, way behind. Some of that light is, and you can't probably see the light from the center because it'll be of all this glare, but the light from most of that galaxy, a lot of it is spread out. And so this is what we call a gravitational lens, and it's the proof that Einstein's theory works, and it's also the proof that we have dark matter, because it turns out that the amount of mass you need to curve the light like this is far more than the mass you see in stars. So that's another story, that's been another lecture of mine. Okay, so moving then onwards to the astrophysics, what do we find? So for the past several decades, we've been conjecturing that there are black holes out there. In the center of this galaxy, one of the more beautiful galaxies taken with a Hubble telescope, the Sombrero Galaxy, there is a black hole of 1 billion times the mass of the sun sitting in the middle. How on earth do we know that? We measure the orbits of stars, and we can infer there's a concentration of mass in the very center. Of course, that in itself is a very indirect argument, but combined with our knowledge of the quasars, which I'll come back to, once these black holes are very active and had to be very compact and only could be black holes. So to summarize where we are in astronomy, we believe that there are black holes weighing tens of solar masses. This is in the realm of stellar astronomy. We measure that by X-rays coming from stuff falling in. And these are the fates of stars that are more 10 or 100 times more massive than the sun. They cannot end up in anything more that's stable. They must collapse all the way to make this black hole. And then we're much less sure about how the big black holes are made, but we're convinced from studying the quasars and other things that there are black holes weighing millions or more times the mass of the sun. So let me begin by telling you about the stars that will make black holes. This is a prediction, really. I'm going to show you some examples of stars that are 100 times or more massive than the sun. And so these pictures are taken with the Hubble Space Telescope. And so this is a region inside the Large Magellanic Cloud, which is our nearest galaxy to us, making lots of stars. The Milky Way is making lots of stars, but many of these are very massive stars. So in the center of this galaxy, and you can see this nebula with the naked eye, actually, just about. It's just a bright spot in the center of the Large Magellanic, which you can also see with the naked eye beautifully in the southern hemisphere. There are two regions where there are star masses have been measured from their luminosities, and we believe there are stars in here that are hundreds of times the mass of the sun. And their fate will be, in a few million years, to collapse to a black hole. We can estimate that time because they're burning energy so prolifically, with the mass they have, they just cannot last that long. I say that long, but in astronomy, a million years is a short time scale. Remember, the Earth is 4.6 billion years old. So this is like the glimpse of an eye. And here's another example also of a massive star that is even in the process of becoming a black hole. So this one, which is called Eta Carina, is a star that's really disintegrating. It's blowing away huge clouds of gas, because when a star gets massive, it becomes unstable and blows off stuff. But the center, which stays behind, will collapse and make the black hole. And that's what's going on. And maybe we would think in even thousands of years, the final collapse might occur here in an even shorter time. That's a prediction. Someone may be around to check that. We don't know. Okay. So en route to a black hole. So these are examples of taken from X-ray astronomy and optical astronomy of the sort of things you can see. So again, a nearby star. This is again a massive star. This is pouring stuff onto it, and from the orbit of this star and from measuring the X-rays, you can infer how massive this is and decide this is on its way to becoming a black hole. And then sometimes these binaries get so close together they disrupt each other, and the only endpoint of these two coming together will be to form a single star that will itself collapse into a black hole, because so much mass gets concentrated when these two big stars merge together. So this is the sort of thing we see. We see these precursors on the way to being the black holes, but we haven't yet got to observing the black hole itself. That will come in a moment. Okay, and then of course these are another example now with the artist's view of the black hole, and you can see the stuff pouring in. This stuff is falling in, getting hotter and hotter as the gravity field builds up. The speed gets higher and higher, not quite the speed of light. It emits copiously in X-rays. That's how we see it with X-ray telescopes. And we learned the only thing that must be there is inferred to be a black hole. Okay, so inference, right? We infer there's a black hole, okay? So here now, let me get to the discovery that really shook the world up in science earlier this year. Okay, so there are two experiments that we're observing. There's a third one, a European one, which is in construction. It's finished. It will start taking data soon, but these are the two that took the data that made the discovery. So replicas of each other. So what we have here is, this is in the state of Washington, the US. This is 4 kilometers, this line. And there's a very powerful laser, okay, shining down these two tubes, okay? These are high vacuum tubes. And there are mirrors at the end, at each end. And so the lasers bounce off hundreds of times, okay? It takes a fraction of a second to do one traversal for the light. And then the light gets added together in the central machine. And the idea is that if a gravitational wave, remember this effect of the collapse starts wiggling space and time a little bit, tiny amount. And I should say that we're looking for an effect over 4 kilometers that's about the size of an atom, not much more, much less, the thinness of a human hair. That's the deviation that we expect, because the wave may strike, this beam before this beam as it goes by. And so when you combine the two beams, you will see a slight offset, which I'll explain in a second. So that's one. And the duplicate, the twin, is in Louisiana and was working at the same time. Again, 4-kilometer long high vacuum tunnel with this laser beam being recombined back here. Okay, so how does this laser system work then? What's the principle behind it? Well, imagine these two arms, let's call them the X and the Y arms of the interferometer, and it's a light wave, that's what laser light is, you think of it as a wave, I have one arm, I have the other arm, and basically they sent out at the same time, it's the same laser, they're in phase with each other, and then when you combine them together, you arrange for them to be exactly out of phase, that they will just cancel each other out. Okay, so the two light rays, because of what we call interference, you put them out of phase, they cancel out. But if there is some impulse in space-time that passes by, that's going to make them not exactly out of phase, and there'll be some light that gets through, and you suddenly start seeing something. That's the principle behind this. Okay. Right, so here is what they saw. And I should say they'd been looking, this experiment was conceived 40 years ago, right? And it's had a long history of funding, ups and downs. It cost hundreds of millions of dollars. In the early days, they were finding nothing. The funding got cancelled from Washington. Protests were made, how fundamental this was, etc. So 40 years went by before they found this amazing result. So that's how hard a team of physicists had to work. And there's almost no doubt that the guys who did this will get the Nobel Prize this year. That's a prediction. Everyone expects that. Okay. And so here is what they then saw. So here are the two black holes, which they in fact saw merging together. And this merger shakes up space and time of the black hole, and these waves come out. And it turns out that it took billions of years for them to get to the Earth. That's because these waves travel at the speed of light. They're a billion or more light years away, way back towards the early universe. It's amazing. It's just because these events are rare. You have to survey a huge volume to find one, which is why they looked for 40 years and found nothing. They just didn't have quite enough sensitivity. So finally, they found one event, and what they saw is as the two black holes come together, this is predicted from the merger of two black holes, this signal, okay? You see them coming together, everything speeds up a bit, and then when they finally merge, there's a big chirp on the shortest time scale. This is and you notice this spacing is how the frequency of light speeding up, of gravity waves speeding up, and oscillating more frequently, and then the end. Okay, and so so you have to imagine that space is doing this. Okay, and that's what's hitting, and so this sort of impulse in space is passing by these laser beams, shaking it up slightly. So this year they've reported finding 3 of these events. Okay, these are this is the first event they saw, and so this is the Washington observer, the Louisiana observer. They see exactly the same thing. Having 2 independent experiments confirms they're seeing something, because these are such difficult experiments that it could be, a passing lorry or something would give you some spurious signal, whatever, minor earthquakes, all sorts of things. The fact that experiments 2,000 miles separate from each other saw exactly the same thing is highly convincing. It also means that you can pinpoint more or less where it comes from in the sky with a lot of uncertainty because you're looking from 2 different angles. Anyway, and then from the spacings of these waves, they could say how far away it was. This is roughly 1 billion light years. And they can tell you how rare they are. And they had to look over billions of light years to find a single event. That's why they're so rare. And they inferred from the spacings of these waves that these were 32 black holes, each weighing 30 times the mass of the sun. Okay, so that was great. That was in February this year. Then a few months later, they announced 2 more detections. So now we have 3 of them. And you'll notice that these are the 3 different detections, and you can see the frequencies are all different for these 3, which means basically they're different masses. Okay, and so because The more massive things sort of move in slightly more slowly, and so you get a slightly lower frequency. And so these are the delays. So these are the three events they saw, and they correspond to masses of anywhere from 30 to 20 times the mass of the sun. And so the amazing thing, as I said, they're measuring the effect of the shift of an atom in size on this 4-kilometer laser beam, which has bounced hundreds of times, effectively 1,000 kilometers, in fact, or a few hundred kilometers. Anyway, so that's where we are. Now, that's the story on black holes that are formed by stars. We've had announced 3 of them. They were actually rather larger. Theorists hadn't quite predicted this. I mean, the theorists who studied the stars said, well, a star like the ones I showed you the pictures of will lose most of its mass, and the black hole it makes should be just a few times the mass of the sun, maybe 10 times the mass of the sun. That's what they predicted. These black holes, the surprise was they were 30 or 40 times the mass of the sun, or 20. I mean, it was larger, and so it's created a lot of excitement in the world of astrophysics. And the explanation seems to be that because these black holes were merging so far away, the universe then was quite young. And when the universe was young, it most likely was chemically much poorer off than it is today. And it turns out that means less oxygen, less everything in the way of heavy elements. And so that means that the stars that made the black holes have a much harder time blowing out, ejecting their mass, as I showed you in the pictures just now of rapidly evolving massive stars. So they would have capped much more, and therefore they made more massive black holes. So in some way, we're even beginning to do cosmology with these first black holes, looking back in the early universe. That is a whole other story, okay? So now, that's what I want to say about the stellar mass black holes. Let's now think about the next step, where we're going next in this black hole chase. Apart from finding many more, there's a whole new dimension that's opening up. And this is another amazing part of the story that will come to reality in a little while, maybe a few decades actually. So this is the center of the Milky Way galaxy. And we believe that lurking in the center, there is a black hole. So how do we know this? These are, the black hole we think is in here, and these are orbits of stars, okay, these lines. And so let me show you, it's been measured now for 15 years. And what you can see are the stars move slightly, right? So these are the orbits of the stars. And because the stars are circling the black hole in the middle, you can just as, the Earth goes around the sun, so you can infer the mass of the sun, the gravity field. And so in this case, the gravity field that controls the speeds of those stars tells you there is a 4 million solar mass black hole in the middle of our galaxy. It's a monster black hole. And this couldn't possibly have come from a single star. And most likely, when that black hole stuff falls into it, it will produce a lot of energy. So that's a prediction that we might expect to test. But of course, we'd like to measure this black hole directly. But it's a tough job because the bigger the black hole, the slower things go. And so, one could measure the formation of the stellar black hole by having these, by measuring the change in over a few kilometers. That requires maybe thousandths of a second, blips in your laser interferometer. These things would occur on much, much slower timescales. So you could no longer use 4 kilometers. That would not be nearly enough. You have to think of something more ingenious, which I'll come to in a second. And so, but that's our own galaxy. And so here is this other galaxy I showed you earlier, the sombrero. And in the middle of this, by the same argument, we infer there's a billion solar mass black hole that is measuring now not individual stars, by effectively measuring the motions of stars with a spectrograph. You can infer they speed up near the middle, and it's inferred there's a black hole there. Okay, so why we're convinced these black holes are there is not so much from these very indirect arguments, but one that's slightly more indirect, which is shown on this cartoon, which is that early on in the galaxy, when the galaxy was forming, these are stars outside our forming galaxy, a gas would fall in, and the black hole would be made at that time. We know they're there. And the black hole will be fed by lots and lots of gas, okay? At the same time, the stars are being made. But when you feed a black hole, you produce huge amounts of energy. This is what we see in the objects we call quasars. And that energy would then basically disrupt the rest of the galaxy. But you'd end up with a galaxy like the one I showed you, the sombrero, huge amount of stars, and a black hole in the middle, now totally inactive, but early on was responsible maybe for explaining the galaxy itself. So that's indirect. What my colleagues can do are make beautiful numerical simulations of this sort of thing. So here's an example of the power of computing. So this is a galaxy much like the Milky Way, okay? And when it has a black hole in, and the black hole started, clouds began falling in, and they released so much energy, there were giant explosions. So you can see these explosions occurring, which puff out huge bubbles of very hot gas and disrupt the medium around it. So that's a conjecture as to what is happening. So does any of this really happen? So here is the proof that it really did happen. So this is the Milky Way, as seen with a satellite that measures gamma rays. And so this was a discovery that was totally unexpected. So if you study this clearly, all these streaks are just gamma ray sources in the sky, the gas in the galaxy interacting with particles and producing gamma rays. In the center, you can see these two big bubbles, a few hundred light years across, one and one. And we believe the only explanation for these two big bubbles is that about 10 million years ago, there was a giant explosion which ejected these bubbles of very hot gas and created gamma rays, which we're still seeing. Okay, so we think that's the relic of what the Milky Way did, and of course the Milky Way has a very modest sort of black hole compared to the billions I mentioned, and things are much more violent in the distant universe. Okay, so, and the way these explosions work, well, let me pass this one and just show you. So here's an example of a much more violent explosion around the black hole, and the black hole sort of basically, as it twists magnetic fields and things in the middle and in the gas falling in around it, a huge jet of plasma gets ejected, okay? So this is, again, a prediction. This is the way you expect to see a black hole feeding energy into its surroundings. And so again, I don't want to dwell on the theory, but what is much more exciting is what astronomers see. So this is a picture taken with a radio telescope, one of the big ones. And here is a very standard sort of galaxy. This is an optical image of the galaxy. And then when you look in the radio, you see these two enormous lobes of hot plasma, okay, emitting radio waves, with these two jets connecting them. And so there's huge amounts of energy involved here, and the only explanation we have is that there is a giant black hole being fed, having some enormous explosion by twisting up its field lines and having them all reconnect, just like you saw explosions of the solar prominences. That's again twisting, reconnecting field lines that give the energy. On a much more violent scale, you can see that in single galaxies. Okay, well, there are many interesting aspects of black holes. Here is just one briefly. And so this is that when two black holes merge together, the chances are that this final burst of energy will come more on one side than the other. And that means that because the explosion pushes you in one side, by something very fundamental to physics, saying that if the energy goes out one way, then the black hole maybe has to move the other, just to balance momentum, basically. And so one thing we expect to see is to be able to measure this eventually with these signals from interferometers and see if black holes get kicked out. We predict they should be, which means there'll be black holes floating in space, not necessarily so far from the Earth, which gets us, to the field of movies like Interstellar, where there was a monster black hole found not too far away. Okay, so they could be lurking nearby. Okay, so now let me end up with telling you this very futuristic experiment, which almost certainly will go ahead. Namely, how do we prove any of this? I showed you how we detect the stellar black holes. Now let's move on to how we detect these monster black holes. So what is the future for that? Okay, so I said that for the stellar black holes, you're taking the time they fall together is a fraction of a second. And that means space starts off oscillating with a frequency of 1,000 hertz a millisecond, between pulses. And that's measurable with a kilometer scale baseline, which you bounce, 100 times to and fro. You can do that on the Earth, okay. But here's the problem you run into. If you want to check a 1,000,000 solar mass black hole, then it's no longer a millisecond, but it's 1,000 seconds. And that means you need a baseline that's 1,000,000 times longer. So you need to go a 1,000,000-kilometer laser baseline. I mean, the Earth, you can't do that, okay? So what is the future for this? Well, here is the amazing project that will go ahead in 2034, okay? A European project. It's been approved. Okay, so here is the sun, okay? Here's the Earth, here's the moon. We're going to put 3 telescopes in space 1,000,000 kilometers apart, okay? Orbiting along with the Earth, going around the sun, okay? Okay, and so here is our massive black hole, 1 billion light years or more away, okay? Forming, merging with another one, sending out pulses of gravity waves. And so it's going to also ripple space and time. And these are laser beams going between these satellites. And you have 3 of them, because 2 maybe is a bit dangerous. You want to have 3 so you can really, check the ripples that go by. And it's going to, again, the same principle. You're going to look for phase shifts, interference in these laser beams. So that's the idea, in principle, of how this is all going to work. And it needs basically being able to measure this change over 50 million kilometers, again, by, talking of changes of order, the width of a human hair or something, right? It's just incredibly precise. But you can do that. I mean, the main problem is, in space, there's things like winds from the sun, right? Plasma around. You have to figure out how to make the satellites exactly drag-free, how they don't respond to their environment. And you do that by suspending a vacuum cavity inside the spacecraft, and you put very accurate sensors in that cavity, and you suspend your mirrors that bounce the laser beams, by without actually using physical connections, just very very thin wires, and you monitor all of that anyway. So 1,000,000 kilometers apart, 50 million kilometers from the Earth, which is itself 96 kilometers from the sun, million from the sun, and then billions of kilometers from where the waves are coming from. So it's all tremendous, okay, I think, and exciting for the future. But 2034 is when you can expect the earliest, given the funding and whether we'll be part of that is Brexit related, I'm sure. So, who knows? It's a big European project. Anyway, so let me try to bring things to a conclusion. So we have many, many theories, okay? And we have very few proofs. And it's wonderful that we finally have a proof of a black hole. When you look at the universe, and this has of course had many, many manifestations in the popular media. This is one of my favorite ones. So there's a black hole lurking in the center. Imagine a spaceship approaching the black hole, and this is actually from the movie, made for the movie Interstellar. And this is an accurate representation of what the universe would look like when you got close to the black hole. You would suddenly see all the stars being distorted, and eventually you would just see this blackness ahead of you. And when you got in too close, light, you'd see nothing anymore, and your only future would be inside the black hole. For the outside observer, it would take forever for this spaceship to get in, but if you're inside, you'd have some hope of getting into the middle. That would happen in a fraction, in seconds or minutes, depending on the mass of the black hole. And what might you expect if you actually get into the black hole? So let me now go into the realm of science fiction, again, that was displayed a little bit in the movie Interstellar. And so here is what you find. Remember, I talked about a black hole curving space and time. Well, now your spaceship, if ever you could build one strong enough, could get into the middle. And there, one speculation, Einstein's theory predicts this, if you like. No one has ever found one. But there could be something called a wormhole, which is sort of the opposite of a black hole, which takes you into another region of space and time. And this is a way of carving a hole through space and ending up somewhere else far away in different times. And this is what we call the multiverse, which predicts that there could be such regions allowed by theory, many different universes, only accessible by such weird machines, if one could ever call that a machine or a technology, using something like a way of penetrating space, not by a wormhole. Okay, let me end. So I love this quote. We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance. That again was John Wheeler, the inventor of black holes. So thank you.